And this integral is taken from MIT 2024 Integration B Final. And I would like to do this one by two methods. So I will just share with you. And these two methods are not including the Feynman's technique. Now, the first method is this. I rearrange the numerator as a natural log e to the x multiplied by 2 minus e to the negative x dx. Yeah, that's obvious. And then this one, it becomes what? I can change the numerator into two. The first one is this, e to the x minus 1, log e to the x, which is x, right? X. And the second one is a plus e to the x minus x, and then log 2 minus e to the negative x. Very good. And I call this one as a J1. I call this one as a J2, right? I just do them separately. The J1 is this one, x e to the x minus 1. Well, I multiply by e to the negative x. So this is 1 minus e to the negative x, and x times e to the negative x. Yeah, since this one in this interval is less than 1, less than absolute value 1, so we can expand this one as a power series. So this one is equal to integral x e to the negative x as the power series, right? As the power series 1 to infinity, and e to the negative n minus 1 x, right? Then dx. See, I couldn't do there because this one is less than 1. Then I can do as power series. Then this one, I can bring this x over there. This is equal to, this will be equal to integral, right? Yeah, x sigma, because each of x combined with this one is equal to e to the negative x from the x. Yeah, good. Very good. Then, since this is convergent, therefore we can exchange the operators. So this one becomes sigma and integral x to the e to the negative x. Yeah, very good. Now here I'm using substitution. Let t be n x. So my x is equal to t over n. Right? So my integral becomes integral x is equal to t over n, then e to the negative t, right? dx is equal to dt over n, right? Times over n. Yeah. Okay. When x equal to 0, t is 0. When x equal to infinity, this is infinity. No change. Yeah. So this one is equal to n squared taken out. Integral t, and then well, that integral is not difficult. So this one is equal to sigma 1 over n squared. This integral, we can write t d e to the negative t, right? And times negative 1. Okay, good. So this is d u dv. So this is equal to sigma of n squared uv, u times v, right? U times v minus v du, so it will become plus v du. V is there, and du is dt. So this one is equal to, this is 0, and when t approaches to 0, it is 0, right? When t approaches to infinity, use L'Hopital's rule. Very easy, it's a 0. So sigma 0, and this one is equal to negative e to the negative 2, right? Yeah, France. So when this one, when it is a 0, when t equal to 0 is a 1, therefore this one is equal to sigma. Yeah. So this is pi square over 6, right? It's Basel. All right, so we find J1. Now then J2. Uh, J2. Where's 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 J1? J2 is this. J2 is this, right? All right, we copied on J2. This is J1, this is J2. From 0 to infinity, natural log of 2 minus e to the negative x, e to the negative x minus 1. Okay, this is my J2. Now I use substitution. Let u be 1 minus x negative. Okay. So e to the x, I move here over y minus u. So it's a reciprocal, right? Reciprocal. Yeah, good. So x is equal to log of 1 over 1 minus. Okay. So this one is equal to what? It's a negative, right? Negative, not. Yeah, good. All right. Now, then dx, of course, dx is equal to what? Dx is 1 over this, right? Yeah, 1 over times the negative 1, which is okay, good. So everything's ready. Everything's ready. This is equal to natural log. I'm going to ask you this becomes 1 plus u. Yeah, that is good. And this one minus this one, 1 over 1 minus u minus 1 times du over 1 minus u. Yeah, when x equal to 0, u equal to 0. When x equal to infinity, u is 1. Good. So this one is equal to integral. This time this one is 1 minus 1 minus u natural log 1 plus u du. Very good. So this one equal to natural log 1 plus u. This becomes u, du. Uh, then I can rewrite the log of 1 plus u as a power series. So this one is equal to 1 over u log 1 plus u is equal to n and 1 negative 1 n plus 1 u to the n. Yeah, du. Okay, so this one equals to integral here from 1, and this u, yes, 1 to infinity. This becomes as n 1 plus n minus 1 un minus 1 du. Yeah, since this one is convergent, therefore we change the operator 1 to infinity. So n is nothing to do with this one. This is yeah. This is n. I'll take n out minus 1 to the n minus 1. This integral is 0 from un minus 1 du. Right, this is okay. This is equal to no, sigma 1 to infinity n minus 1. This integral is n, right? U to the n. Yeah. Yeah, this is right. So this one is equal to 1 under n. So this sigma 1 plus square negative 1 to the n minus 1. Okay, what is this? Well, that one is equal to, it's alternating. Now, let me write it. When n equal to 1, it's a 1. N equal to 2 is negative 2 square, then positive, then negative, then positive, then negative, and so on. So this one is actually equal to this series, taking away negative, negative is an even power, right? Even power is this, 2n. That's even power. But you take a 1 is not enough. You have to take a 2, then make up this series, right? If you take a 1 only, it becomes a 1, 3, 5, and so on. You have to take a 2, you take a 2, then come up this series, alternating. So this one is pi square over 6 minus 2. This one is a 1/4 over 1/4 over pi square over 6. Yeah. So finally, this one becomes pi square over 6. This is half, right? 12 pi square over 6. So this is equal to 12 pi. So this is my J2. My I is equal to J1. This is I. J1 plus J2. And the J1 is this. I did. So this one is equal to J1 plus J2 is pi over square over 6 plus pi square over 12. That is equal to pi square over 4. Yeah, good. Okay, it's done by method 1. Now then, let me do method 2. Method 2. The integral is this, right? 0 to infinity, natural log 2 e to the x minus 1, e to the x minus 1 dx. Okay, this is my integral. Method 2. I'm using substitution, e to the x as my 1 minus 1 over my 1 minus t. So x is equal to log 1 over 1 minus t. Right? So then this is equal to what? X is equal to negative log 1 minus t. And then dx is simply mean this over this, right? Times negative 1, cancel this negative, so it becomes negative t. Yeah, okay. So my integral becomes integral, it's 2, right? Natural log 2 over 1 minus t minus 1. This is a t, yeah? And 1 over 1 minus t minus 1. Dx is dt minus t. Okay. When x equal to 0, t equal to 0. when x equal to infinity, so t equal to 1. Yeah. All right, then this becomes, this cancel 1 minus t. This is a natural log 1 minus t, 2 minus 1 plus t, right? And a dt. So this one equals to 0 to 1. This is a t now. This is log 1 plus t and 1 minus t dt. Wow. Okay, it's clear. Then this one is equal to 0 to 1, 1 over t. Now log this, I can write natural log 1 plus yt. T is from, y is from -1 to y equal to 1, right? When y equal to 1 is log 1 plus t. Y equal to -1 is minus this. Yeah, that's okay. So this dx. Yeah. So this is actually a definite integral. This 1 over t. This is a definite integral for y with respect to y. The integrand function is the derivative of this one with respect to y. So this is 1 plus yt times the derivative of this one with respect to y times t dy and dt. Yeah, very good. So this one equal to 0 to 1 and 0 to y. This is tt cancel out, right? Becomes 1 plus yt dy dt. Yeah, this is a double integral, so I can switch the order. So I do. No, well, this is 1. This is 1, right? What? I'm sorry. This is negative to positive 1. Okay, so I switch the order of the integral. Then I do this one. 1 plus yt dt, then dy. Yeah. Well, then this one is not difficult. This one is not difficult. This is 1 plus yt and d 1 plus yt and just simply divided by y. Yeah. This is a dt, yeah? This is dt, then dy. So this one equal to net. This integral is a natural log 1 plus yt, right? Yeah, over y. T is from 0 to 1 and dy. Okay, continue. And this is equal to t, yeah? This equal to log 1 plus y over 1, right? Minus log 1 is 0. See, then dy. Okay, good. Then then I express 1 plus log y, log 1 plus y as a power series, 1 to the infinitive n and negative 1 to the n minus 1 y n. Yeah, here one. This power series is the expansion of a log 1 plus y. Then y combined. So this is sigma n minus 1 y n minus 1. Yes, this power series is convergent, alternating, right? Alternating. Then I can switch the operator. So this is 1 to the n, 1 plus 1 over n. And negative 1, I take this one out too. Okay. So this integral from minus 1 to 1, log n minus 1 dy. Yeah, this one is equal to n. This one is y over n, right? Right. y n over n is negative 1 to 1. Yeah, this one equals sigma negative 1 to the n minus 1 n. Well, the first one is 1 over n. The second one is negative 1 to the n. So we have two series. The first one is alternating n square. The second one is n square, and a negative one. This is becomes a negative 1 to the 2n, times negative 1 to the negative 1. This one and that one combined to this. Take one, yeah, that's correct. So this one, as we did in the method of one, this is this, right? This we have done it. Yeah. This one's negative. This one is positive. So this is positive actually. Yeah, that's correct. So this one is pi squared plus pi squared over 6. So this one is equal to pi squared over 4. Wow. This is done by method 2. Wow, very good. Very, very good. Now, these two methods are not including the Feynman's technique. Thank you.